Imagine just traveling across these huge cosmic distances in like seconds, stepping through a gateway like walking through a door.
Sounds like total science fiction, right?
Totally. But today, we're actually diving deep into the real science behind concepts like traversable wormholes
Yeah.
and stargates.
Yeah, and it's fascinating because this isn't just, idle speculation. We're actually digging into a defense intelligence reference document.
Exactly. A serious document looking at faster than light travel using these space-time
It's
shortcuts.
pretty wild stuff.
So our mission today for you listening is basically to unpack all this, the science, the big challenges, what might actually make it possible. Traversable wormholes,
I
stargates.
want to give you a clear picture,
Yeah.
sort of separate the fact from the fiction without drowning you in jargon.
Right. And we'll be hitting on this core idea, this almost unbelievable concept called exotic matter.
Ah, yes. Stuff with negative energy density. Sounds weird, I know.
It does, but apparently it's absolutely crucial for these shortcuts. It's kind of the key ingredient.
It really is. Okay, so where does this whole idea of traversable wormholes even come from?
You might think Hollywood, but no.
Not at all. It's actually rooted firmly in Einstein's general theory of relativity.
Which is pretty mind-blowing already. But the story gets better.
Oh, yeah. The sort of modern concept, it came about back in 1985. Some physicists at Caltech, Morris and Thorne.
And they weren't just like brainstorming FTL drives, were they?
No, not initially. It was, get this, at the request of Carl Sagan. He was writing his novel, Contact.
No way. For the book.
Yep. He needed a scientifically plausible way for his characters to travel interstellar distances quickly. So he asked these experts.
That's incredible. So a sci-fi plot point basically kicked off serious research into wormholes.
Pretty much. That academic exercise sparked real research into traversable wormholes and even the possibility of time machines.
Okay, so define a wormhole for us in this context.
Basically, think of it as a theoretical tunnel, a
Yeah.
shortcut through hyperspace. It connects two really distant points in our universe.
Or maybe even other places.
Potentially, yes. The definition can stretch to connecting different universes, maybe other dimensions, or even different points in time. Though the time travel aspect is a whole other can of worms we're mostly setting aside today.
Right, focus on space travel for now. But it's important, isn't it, to distinguish these from black hole-related wormholes?
Absolutely crucial. You have the Einstein-Rosen bridges or Schwarzschild wormholes. Those are linked to black holes.
And those are bad.
Well, you can't travel through them. They have a singularity at the center, infinite density, crushing gravity. Nothing gets through. And an event horizon, the point of no return.
Okay, so not exactly a convenient subway system.
Not at all.
Huh.
But a traversable wormhole, the kind Morris and Thorne conceptualized. That's different. No singularity, no crushing gravity. You could theoretically pass through safely. No event horizon either.
Phew. Okay, and then there's this Stargate idea. What makes that special?
That's pitched as a sort of refined version. The main difference is the entrance and exit they're imagined as flat.
Flat, like a door frame.
Kind of. Instead of a spherical opening, imagine a flat plane you step through. The physics are also thought to be, well, simpler in some ways.
Easier to handle, maybe?
Potentially. The document has a figure, figure 1, that shows an intra-universe wormhole as a shortcut. You can see how it bypasses the vast distance of normal space.
Yeah, you can see the appeal immediately. Just hop through.
Which brings us to why we'd even bother thinking about this. Why look for these shortcuts?
Because getting around the normal way is hard.
Extremely hard, especially between stars. All our current propulsion ideas, even the fancy non-traditional ones, are based on Newtonian mechanics, pushing stuff to go forward.
Action reaction.
Right. And for interstellar distances, this means you need ridiculous amounts of fuel. The mass ratios, the ratio of fuel mass to payload mass become astronomical.
Like needing more fuel than stars in the galaxy just to send a probe somewhere reasonably fast.
Maybe not that bad, but the numbers are staggering. We're
Like-
talking ratios of 10 to the 5th, maybe 10 to the 100th power. For trips within a human lifetime, it's just not practical.
You end up carrying fuel just to carry more fuel.
Exactly. And even if you could somehow get close to light speed,
Uh-oh. There's a catch.
time dilation, Einstein again, clocks tick slower for the travelers compared to Earth.
So the crew has a quick trip.
But centuries could pass back home. They return to a world they don't recognize. Loved ones gone. History moved on.
Oof. Yeah, that's a major drawback.
Which is why wormholes are so appealing. Instantaneous travel, essentially. You bypass the distance and the time dilation problem.
Pop over, pop back. Maybe even, as the document hints, return before you left.
That's the time machine aspect again. Super weird. But yeah, theoretically possible with some wormhole configurations. But let's stick to space travel for now.
Okay, so wormholes solve the travel time problem, but there's always a but.
There's a big but. Engineering spacetime like this, according to general relativity, needs something very specific.
Here comes.
Exotic matter.
Right, the stuff with negative energy density. What is that, really? It sounds impossible.
It does sound impossible, I know. But negative energy here doesn't mean like anti-energy or something that repels gravity necessarily. It's defined relative to pressures and tensions in the space-time fabric.
So, less than zero energy. How does that work?
Think of empty space, the vacuum, as having zero energy density baseline. Normal matter has positive energy density. This exotic matter would need to have an energy density below that baseline 0.
Like being overdrawn at the energy bank?
That's actually a decent analogy. It's a deficit relative to the vacuum. And sometimes it also needs negative stress tension, which is like an outward pressure pushing space-time apart to keep the wormhole throat open.
Okay, still sounds weird, but maybe not magical. But doesn't this violate some fundamental rules of physics, these energy conditions you hear about?
Yes. The standard energy conditions. Weak, null, strong, dominant energy conditions. They essentially hypothesized that energy density should always be non-negative locally.
And exotic matter obviously breaks that rule.
It does. And for a long time, that was used as an argument against the possibility of things like traversable wormholes or FTL travel.
Yeah.
See, it requires violating energy conditions. Therefore, it's impossible.
But the document we're looking at says that's not quite right.
Exactly. It calls it a spurious issue because those energy conditions, they're hypotheses, not proven fundamental laws.
Really? They're not set in stone?
Nope. And here's the kicker. We already know they can be violated. Quantum effects allow for it.
Quantum mechanics messes things up again.
Or rather, reveals a deeper reality. Quantum field theory predicts, and experiments have even hinted at, states with local negative energy density or negative energy fluxes. It's been known theoretically since the 60s.
Wow. So nature itself might be okay with negative energy, at least locally.
It seems so. And furthermore, there are proofs showing that any traversable wormhole spacetime must violate some energy conditions. It's a requirement. So needing exotic matter isn't a bug, it's a feature, you could say.
Okay, that changes things. So violating these conditions isn't a showstopper, but does it cause other problems? If these conditions are usually assumed in physics.
That's a very good question. It's an active research area. If energy conditions can be violated, it might open the door to other strange possibilities, maybe challenges to causality, things like that. But the fact that quantum mechanics already includes these violations suggests our classical understanding might just be incomplete.
Right, we need that quantum gravity theory, which we don't have yet. Okay,
Right.
So let's assume we can have this exotic matter. What would a wormhole actually look like if I stumbled upon one?
Depends on the type. The classic Morris-Thorne spherical wormhole, the entrance would probably look like a sphere,
Just a floating ball.
a very weird ball. Inside, you'd see a distorted, shrunken mirror image of the other side, wherever the exit is.
Like looking into one of those reflective garden globes?
Sort of, yeah, but showing a distant place, maybe another universe, all warped. It's called topological inversion. Figure 6 in the doc gives an idea.
Wild. And the flat-faced Stargate type.
That's theorized to be much less visually confusing. Because the exotic matter is arranged differently, it supposedly has zero net effect on light passing straight through.
So, like a window.
More or less.
Yeah.
You just see the view on the other side, undistorted, like looking through an open doorway into another region of space. Figure 7 and 8 illustrate this.
That definitely sounds more user-friendly. The document also mentions something about how a small wormhole might appear if it, like, popped into existence nearby.
Yeah, that's an interesting bit.
Yeah.
It suggests that if a small wormhole intersected our space, it might appear as a really bright spot in the sky.
Bright spot. Okay.
And if its size changed, you might see Doppler shifting. It would shift toward blue if growing, red if shrinking. A very unusual signature.
Huh. Something astronomers could potentially look for, maybe.
Perhaps. Okay, so we need this exotic matter, this negative energy stuff. Where could we possibly get it? That's the million-dollar question, isn't it?
Yeah, all right. Sources of negative energy. What does the report say? Lasers.
Lasers are mentioned, yes. Specifically, using ultra-intense lasers to create really strong static, electric, and magnetic fields. These fields can have negative energy densities.
But there's a catch.
The challenge is generating enough tension within those fields. So, possible in principle, but Hard to scale up, it seems.
Okay, what else? You mentioned quantum stuff earlier.
Right. The squeezed quantum vacuum. This is a really fascinating quantum optics concept.
Squeezing the vacuum. How?
The vacuum isn't truly empty, right? It's full of quantum fluctuations, zero-point energy. Squeezing means manipulating these fluctuations. You can reduce the uncertainty or noise in one property, like energy.
At the cost of increasing it somewhere else. Heisenberg uncertainty.
Exactly. And if you squeeze the energy fluctuations below the normal zero-point level, that region can momentarily have negative energy density.
Whoa. So you can borrow energy from the vacuum, creating a deficit.
Kind of, yeah. The document describes ways to do this conceptually, using lasers, optical resonators, maybe rotating mirrors or special gas chambers to separate out pulses of negative energy.
And this isn't just pure theory.
No, there have been lab experiments demonstrating squeezed vacuum states using diode lasers and atomic vapors, things like that. So we can create these states, at least on a small scale.
Okay, that's genuinely mind-blowing. Manipulating the quantum vacuum itself. What's next on the list?
Gravitationally squeezed vacuum.
Gravity squeezing the vacuum.
Yeah. The idea is that really strong gravitational fields, like around black holes or maybe neutron stars, could distort the quantum vacuum fluctuations, the ZPF, creating zones of negative energy naturally.
So space itself could create this stuff near massive objects.
Theoretically, yes. It came out of quantum field theory in curved spacetime. The stronger the gravity, the stronger the predicted negative energy zone. Table 1 shows estimates for Earth, the Sun, black holes, even protons.
Protons? Really?
Yeah, protons are predicted to have a surprisingly strong effect locally due to their density. But there's some debate. Different calculations give different results, like this discrepancy noted between Hochberg, Caffard, and Ford.
So, still theoretical wrinkles to iron out. And we can't exactly make black holes in the lab to test it.
Not currently, no. Artificial gravitational squeezing is unknown territory.
Okay, last big one. The Casimir effect. I feel like I've heard of this.
You probably have. It's the most experimentally verified source of negative energy density.
How does it work again? Something with plates.
Exactly. You take two parallel uncharged conducting plates, put them very close together in a vacuum. The plates restrict which quantum vacuum fluctuations can exist between them compared to outside. Fewer modes means lower energy density between the plates.
Lower than the vacuum outside. So negative relative energy density.
Precisely. And this creates a tiny, measurable, attractive force between the plates. It's real. It's been measured.
Wow.
Yeah.
Okay, so we can definitely make negative energy density this way.
Yes, small amounts.
Ah.
The document mentions variations too, like topological Casimir effects for other fields, and the dynamical Casimir effect with moving mirrors generating negative energy flux. But that's currently very weak.
Could we use the standard Casimir effect to build a wormhole?
People have theorized about it, maybe arranging plates spherically, but the calculations suggest you'd need incredibly tiny separations, like smaller than an atom.
Uh-oh. Problems.
Big problems.
Yeah.
At that scale, other forces like van der Waals forces dominate, and just physically making such structures is beyond us.
Right. So we have potential sources, some proven, some theoretical, but scaling them up seems to be the issue, which leads to the difficulty of actually building one.
Yeah, the document is titled Not Easy for a Reason. The initial calculations were pretty daunting.
How daunting.
Using what's called the thin shell formalism, early estimates suggested you'd need negative energy equivalent to the mass of Jupiter.
Jupiter, just to make a 1-meter wormhole.
Something like that, yeah.
Yeah.
Table 2 shows these kinds of huge numbers. It looked completely impossible.
Okay, yeah, that sounds like a showstopper right there. Packing Jupiter's mass worth of negative energy.
But, and this is a huge but, the document points out this is equivalent mass, and general relativity is nonlinear. The total actual mass of the system might be much less, maybe even zero or positive.
Wait, how can negative energy have positive total mass? That sounds weird.
It's the complexities of gravity warping spacetime. Energy curves, space-time, and that curvature itself has energy. It gets complicated. But the really exciting part is more recent research.
Hold on.
Research using things like the Gauss-Bonnet theorem, which relates geometry and topology. It suggests that traversable wormholes might be possible with arbitrarily small amounts of negative energy.
Arbitrarily small, as in tiny amounts, not Jupiter's mass.
Exactly. Potentially incredibly small amounts, strategically placed. This completely changes the outlook. Suddenly, it seems less impossible, maybe achievable someday.
Okay, that is a game changer. That makes the whole prospect seem vastly more plausible, even if still incredibly difficult.
It does. It shifts the focus from needing impossible amounts of negative energy to meeting exquisite control over potentially tiny amounts.
The document also mentions a weird mass conservation thing when stuff goes through.
Yeah, a specialized conservation law. When mass goes in one mouth, that mouth gains mass, and the exit mouth loses an equivalent amount. It hints at potential limits on how much mass can traverse, maybe needing a reset. Very strange stuff.
Like the wormhole needs to rebalance itself. Okay. Now, what about these quantum inequalities? Are they hurdles?
They were thought to be. The QI conjecture basically tries to put mathematical limits on negative energy. Like, you can only have it for a short time if it's strong, or it needs to be balanced by positive energy nearby.
So nature trying to prevent too much negativity.
Sort of the idea. If QI were universally true and strict, they could forbid macroscopic wormholes.
But
Again, the document highlights issues. Firstly, they haven't been proven universally, especially not in curved spacetime or for interacting fields. Secondly, known negative energy sources like the Casimir effect and squeezed vacuum states seem to violate them.
so the things we know can create negative energy don't obey the supposed rules limiting negative energy.
Seems that way. There are even specific theoretical counterexamples, like Krasnikov's work related to FTL spacetimes. And researchers like Visser have shown that the total amount of energy condition violation needed for a wormhole, when integrated over volume, can be made arbitrarily small, offering a different way to quantify it that avoids the QI issues.
Okay, so the quantum inequalities might be interesting theory, but maybe not a fundamental roadblock in practice. Good. How about finding this stuff? Can we actually observe negative energy or wormholes?
Theoretically, yes. As we touched on, negative energy should act as a gravitational lens, but differently than positive mass energy.
The weird lensing effects?
Right. Unique distortions, color shifts, chromaticity, changes in brightness, it would have a specific signature. Astronomers could look for background objects being lensed in this characteristic way.
And they are looking.
There are searches, yes. And as mentioned, some computer simulations of negative energy lensing apparently look a bit like some observed gamma ray bursts.
Intriguing. Not proof, but interesting.
Definitely. Negative energy lensing could create effects like a central shadow and umbra, with bright rainbow-like edges called caustics. Maybe even brighter lensing than positive mass in some cases.
Cool, but hard to do in the lab, you said.
Scaling down astronomical techniques is tough, but there are other ideas for lab detection.
Like what?
One proposal by Davies and Ottewell uses particle detectors that can be switched on and off. The idea is that their interaction rate, specifically their de-excitation or cooling rate, might be enhanced by nearby negative energy density or flux.
So negative energy makes things cool down faster.
That's the prediction from their model, though it's based on perturbation theory and might be model dependent. Another idea from Marecki uses sensitive optical detectors, balanced homodyne detectors.
What would they do?
They could potentially directly measure the quantum vacuum fluctuations themselves, and maybe even map out the negative energy profile inside, say, a Casimir cavity.
Okay, so we're getting closer to maybe having tools to really measure and map this stuff in the lab. That feels like progress.
It does. It feels like we're moving from pure theory towards potential experimental handles.
So summing up, what's the way forward? What does the document suggest we need to do to make traversable wormholes a reality, or at least demonstrate them?
Well, it draws a hopeful parallel with nuclear physics took decades of work, but look where we are. Sustained effort is key.
And it mentions potential game changers.
Yeah, like if we finally crack quantum gravity, a complete theory might totally change the rules, maybe even eliminate the need for negative energy if gravity turns out to be an emergent phenomenon.
Emergent gravity, meaning it's not fundamental.
Exactly. The idea that gravity isn't a basic force, but arises from more fundamental quantum processes, maybe from the quantum vacuum itself. If space-time is emergent, then maybe manipulating it doesn't require exotic matter in the way general relativity currently suggests.
Wow, that's a whole other level of mind-bending. But for now, sticking with current physics.
Sticking with quantum field theory and general relativity, the new-term path involves several key research areas.
Okay, lay them out.
1. Generating negative energy. We need dedicated programs to build better squeezed vacuum generators, explore different Casimir effects more deeply, understand the dynamical Casimir effect better, look into other quantum sources like Dirac field states.
Basically, get better at making the stuff.
2. Detecting it. We need to refine those lab-scale detection methods, the particle detectors, the homodyne detectors, maybe scale down astronomical ideas.
Find it and measure it accurately.
3. Trapping and storing it. If we can make it, can we contain it where we need it? This might go hand in hand with detection research, though the author of the document seems to prefer free space sources.
Right. And finally,
4. Actually constructing the wormhole. This is still mostly theoretical. How do you use the negative energy you've generated, detected, and maybe trapped to actually warp space-time into a wormhole? Do you inflate one from the quantum foam? Punch a hole? We'll likely need empirical studies once we have strong enough sources.
okay. So a lot of work ahead, but maybe not fundamentally impossible based on current understanding, especially with that arbitrarily small energy breakthrough.
That's the feeling you get. It's incredibly challenging,
Mm.
but the theoretical barriers seem less absolute than they once did.
So while actually stepping through a Stargate to, I don't know, Alpha Centauri might still be firmly in the realm of science fiction for now, the science itself is real and it's being worked on.
Actively explored, yes. Which makes you wonder, doesn't it? What's the next big breakthrough in quantum physics going to be? Could it unlock space-time manipulation?
Could we really harness the quantum vacuum someday? Use it to bridge the stars? It sounds almost poetic.
And imagine if we did detect a natural wormhole signature out there through lensing.
Yeah,
What would that tell us about the universe? About its fundamental structure?
yeah. The whole journey into this science is just amazing. It really shows human curiosity, right?
Mm.
Pushing the boundaries.
Absolutely. It's complex. The path is definitely not clear. But the fact that we're even having this conversation based on serious scientific documents,
Mm.
it suggests the limits of possible might be more flexible than we think.
Maybe the universe is even stranger and more accessible than we imagine.